let me actually introduce Aaron. So I'm very excited to present Aaron Sternbach as our JQI seminar speaker today. So he's the latest addition to the condensed matter faculty at UMD. He did his PhD and postdoc with Dmitry Basov at Columbia, and he is the kind of person that likes to develop new methods for doing optical probes of solid state systems. So nano resolution, sub-diffraction limited imaging, and also fast pulse measurements of condensed matter. And so he's going to be telling us about the series of experiments that he did. And, he's a very exciting new addition to our greater AMO community here at UMD. And so with that, let me hand it over to Aaron and try to clear the screen of annoying Zoom messages.
Sure, thank you. And this is the microphone. Okay. Let's see if I can clip that on. Also, just for the, I guess, office hours, for those who aren't familiar, my office is PSC 2154. So legible.
Just around the corner from the normal lunch spot.
Yeah. Okay, so without further ado, I'll get started talking about some of our work exploring the insulator to metal transition in vanadium dioxide with time-resolved near-field spectroscopy. Before getting started on the science, since my trajectory leads here to UMD, I figured it would be appropriate to talk a little bit about my background. So I was born and raised in New York, and then did my undergraduate studies at Boston University, where I spent some time working with Richard Averett, and this was really my inspiration to pursue condensed matter experiment. I ended up moving to San Diego to study with Dmitry Basov as a PhD student, and in the midst of the PhD, Dmitry moved back to Columbia. So as Alicia said, my PhD is actually from Columbia, and I continued on as a postdoc with Dmitry before coming here to Maryland to start a group. And Maryland is a beautiful state. We're just north of Washington, D.C., and looking out at, for example, the momentous, giant, beautiful Washington Monument, I thought this would be an excellent place to start a scanning probe lab. So while it's on slightly different scale, the geometric likeness is maybe inspirational. So why are we doing near-field optics? Well, the short answer is that you would like to study the properties of materials with low energy radiation. So radiation approaching terahertz frequencies, where there are hallmark resonances of different properties of these materials, whether it's the electronic conductivity or lattice vibrations or magnetic resonances. However, the low energy of this radiation comes together with a long wavelength, and so normally you have a diffraction limit that limits the spatial resolution, prohibiting observations of inhomogeneous systems and other things. So there's at least 4 good reasons to couple these techniques to AFM antenna, where you can get access to 10 nanometer spatial resolution independent of the wavelength of incident light. The first is that a lot of systems are naturally inhomogeneous. This includes phase transitions that develop inhomogeneously, as well as just imperfections. For example, in 2D materials, there's often wrinkles, bubbles, twist angle, inhomogeneities, and so on. And these impact area average measurements, even though you are, in a sense, blind to them when the wavelength is too large. The second is that in many cases, especially when you're dealing with 2D materials, the entire size of your sample may be smaller than the wavelength of light that you would like to use to address certain phenomena. So maybe somebody in the audience recognizes this image. This is from the famous 2018 paper on twisted bilayer graphene, where it was revealed that this tiny region was superconducting. And one has to overcome twist angle inhomogeneities to observe these kinds of physics. In this particular device, you can see the entire size of the sample is small. And so if you wanted to look at low energy properties, for example, in the terahertz, this would normally be difficult to impossible. So another reason is that this tip not only gives you spatial resolution, it also gives you the associated momentum to launch modes known as polaritons, where you have a hybrid of infrared radiation and collective modes in the material, which are dipole active. This can be plasmons. So this image shows plasmons propagating over tens of microns from a gold disk to the AFM tip. And you can see these oscillations in real space. And that is of interest for several reasons. First, this gives you a way to confine light to the nanoscale and play with subdiffraction limited photonics, but these modes also give you direct information about the properties of the material. This is a probe in a sense of the dielectric tensor of the material that hosts these waves. And finally, when we use pulses of light, we can come in with a pump to change the state of a material, and then come in with a probe at a variable time delay in order to directly resolve how the system evolves from one state to another in real space and in real time. And this, yes?
In that top right picture, is there a phase trigger that you're using to get the wave?
So this is a great question. So the phase is essentially because the wave propagates with a fixed velocity. The phase is set by the distance between the launcher, which is, for example, the tip, and a reflector, which is the gold object.
You're beating it against.
Yes, it creates an interference pattern, and that phase or the standing wave varies from constructive to destructive interference as the distance between the objects change. You can also measure the near field phase and see essentially how this wave is evolving.
So I think of this as a cavity. The resonant frequencies are determined by the position of the tip, and then getting resonant excitation of that cavity.
Yes, yes.
And that's by mapping that signal into the spatial profile where the tip is.
Yes, and
that's how that map is generated.
Essentially, yes. And in the systems where the size of the material that is hosting this wave is confined or limited, then you can actually see, specific cavity modes emerging. In this case, the sample is semi-infinite, and so it's really just the two objects that are creating the cavity. Yes?
Explain why the resolution is independent of the
Well, so the short answer is that what is happening is the infrared light comes in and it polarizes the tip, and there's an evanescent field at the apex of the tip, which is confined to the tip's radius of curvature. And this near field is isolated from background radiation by tapping the tip up and down. And we demodulate the scattered signal at harmonics of that tip tapping frequency so that we can essentially pluck out the component of the field that is evanescent or localized to the radius of curvature of the tip. And while the ratio of that field to background may be somewhat wavelength dependent, the resolution that we get after this performing this procedure is not. We get resolution that is given by the radius of curvature of the tip, independent of the wavelength of incident light.
The Fourier transform that evanescent field, you get components and the X-ray.
You're talking about frequencies. What the frequency is fixed by the incident field. We're not changing the energy in this experiment. It's not a nonlinear experiment. There are components of the momentum which extends to much higher momenta. So the actual peak of momenta that we're sensitive to is 2 pi over the radius of curvature of the tip. And so this does extend to higher momenta, but the frequency is fixed. We're way away from the light cone, is maybe the way to say it, yes.
question has to do with near field versus far field.
Uh-huh.
Situation. I think it's confused with the near, but there is no reflection.
Okay. Well, I guess has your question been answered, or is it? Okay.
And since we're interrupting, I'll ask another quick question. Usually when you have the wavelength really large, it's hard to get it coupled to, like, what accounts for the strong coupling to the tip?
Okay, so this is a fantastic question, and maybe I'll allude to this, and I have one slide at the end talking about what we're pursuing here at UMD. So the tip is an antenna. And this antenna can be much larger than the wavelength of light, which is the mode we typically operate in the mid-infrared, in which case you can be in a quasi-static limit and still get enough signal in your scattered channel and be happy. The dynamic range suffers as you go to even longer wavelengths in the terahertz, and so people do try to use antennas that are resonant with the terahertz light to enhance the local fields, and that creates various complications and makes those measurements kind of difficult. But as long as the signal is large enough, basically if you have enough light coming in and your detectors on the other side are sensitive enough, then you can just use very long antennas and you're okay. Okay. So in order to address these problems, we're developing a system at UMD where we can couple mid-infrared light into the tip and do near-field spectroscopy at a pixel. We can also couple in visible light and do imaging or terahertz light, and we're developing methods based on electro-optic sampling. And so we can measure a variety of things, emission, spectroscopy, or imaging signals across the electromagnetic spectrum, all with 10 nanometer spatial resolution. And since these are all pulses, we can come in with another pulse of light at a variable time delay and do pump probe measurements. Well, the system we chose, and which is here at UMD, has pretty high field strengths, so we can get field strengths in excess of about 5 megavolts per centimeter in free space at all wavelengths up to about 12 microns. The tip gives you an additional boost, which is known as field enhancement. So the fields are enhanced by a factor which is thought to be really large. So at terahertz frequencies, this factor is thought to get up to, say, 10,000. Although this is not something that's measured, this is something that's inferred from finite element simulations, but this is something we're interested in exploring. And so in today's talk, I'll be giving an overview of one way or one system which this kind of measurements can be used for. So that's the inhomogeneous insulator to metal transition in vanadium dioxide. So we'll be looking at this transition as well as femtosecond snapshots of this transition and addressing different systematic measurements to try to understand what are the origins of the inhomogeneous phase progression that we observe. We'll then talk about some of the evidence that points to this inhomogeneity coming from pre-existing factors or features in the film. And then briefly, I'll mention how we've collected evidence suggesting that we can anchor the insulator metal transition intentionally by providing field enhancement with metamaterials. Last, I'll talk about some of the directions that we're interested in pursuing here at the University of Maryland. So vanadium dioxide is a correlated electron system. It goes through an insulator to metal transition at a temperature of around 340 Kelvin. And together with this electronic transition, there is a structural transition from a monoclinic structure to a rutile structure that occurs around the same temperature. There's sort of a chicken and egg question, which has been studied for decades now, of if it is the electronic transition that drives the structural transition, or if it is the structural transition that drives the electronic transition. And various perspectives have been given on this problem. One of the features, however, that you can see in this measurement of resistance is that the resistivity changes in a way that appears to be continuous rather than abrupt, which is surprising for a first order transition. And so in this talk, we're not even going to get to the electronic versus structural transition. We're really just going to be focusing on the electronic transition, the role of nucleation in growth, which is still something that is we're just learning how to address. So the resistivity is perhaps a natural way to look into the electronic properties of this system. The optical conductivity at low frequencies gives you a measurement that should agree with your DC resistivity. At higher frequencies, the optical conductivity is impacted by scattering and interband transitions, and so you see some structure. What you can clearly see is that this blue curve, which is the insulating phase with low conductivity, and this pink curve with metallic-like conductivity are attained below and above the insulator metal transition temperature, respectively. However, when you're in the vicinity of the transition at intermediate temperatures around 340 Kelvin, you see values of the optical conductivity which are intermediate, which is surprising, again, because this should be a first order phase transition. And so one thought was maybe this is inhomogeneity. So the system maybe is at a local site, it is a pure metal or a pure insulator, but because there is an area averaged composition of insulator and metal, you're seeing intermediate values of the conductivity when you measure these spectra. So yes.
Is this a film, and what's the substrate if it is a film?
It is a film. What's it called? And the substrate is sapphire.
Okay.
And that is very important because in bulk crystals, you do see a sharp first order like transition. Yeah. Okay. So what's it called? In these films, what we do to address the inhomogeneity is we pattern a gold bar on top of the film. Let me see if I can. And this gold bar has a scattering amplitude which is large, characteristic of a metal. And we compare the scattering amplitude on the film of interest. A low scattering amplitude is characteristic of an insulator, and a high scattering amplitude is characteristic of a metal. As we increase the temperature, what you can see is that the scattering amplitude, and thus conductivity, increases to a value that is close to what we observe on gold. This does not happen homogeneously. So we see droplets of metal that grow and coalesce, and the size of these droplets is subdiffraction limited. So we would be blind to all of this with far field optics demanding this near field approach. So all of this was done and known back in 2007. So this was the work of Muntaz Kazılbaş, although I'm showing my own data. What we've done is to adapt this measurement to operate with pulsed sources. So we're measuring these maps now with a pulse of light that arrives in the 200 femtosecond burst, and that allows us to initiate the transition with another pulse of light and monitor how these images evolve as we change the pump probe time delay. And what we can see is that the transition is clearly inhomogeneous and evolves over a timescale of hundreds of picoseconds. So while this map gives you some impression that the transition is inhomogeneous, I want to highlight some of the subtleties. First, this is a stroboscopic measurement. So what we're doing is we're coming in with a train of pulses at a megahertz repetition rate. And this image is collected on a much, much longer time scale. So we spend a few milliseconds at every single pixel. And then we raster scan and collect data and 200 by 200 pixels to form an image at one time delay. And so this whole movie involves a sequence of pulses that is approximately 400 million different pump probe events. And so the only thing that we can see are regions that reproducibly become more metallic at a given location. So you should think about an increase of signal as suggesting that the probability for a given location to become metallic at a given time delay is higher. Okay, it is not necessarily going to tell you the exact single shot conductivity in a given pump probe event. Nonetheless, we can use this measurement to learn about how the system evolves from an insulator to metal. So while this movie is nice to look at, you can perhaps see a little bit more detail if you just focus on line traces. So how the system evolves as a function of a single parameter at a single time. So first, we can look at the change in scattering amplitude, which you can think about as suggesting this conductivity as a function of the pump probe time delay. First, the scattering amplitude rapidly increases, and then there's a relaxation on a sub-picosecond timescale before there is a follow-up growth. And it's this follow-up growth that is inhomogeneous. So to make that point a little more clearly, we could park at a time delay of 250 femtoseconds after photoexcitation. So this is just after the pump pulse has arrived. And look at how this change in scattering amplitude depends on fluence. What we see is a nice linear increase in the near field amplitude that extrapolates to zero fluence. And that's consistent with a linear injection of electron hole pairs. Interestingly, the slope is the same at two locations where we see inhomogeneity at later time delays and above the fluence threshold.
What is fluence?
Fluence is essentially the number of pump photons. So how hard are we hitting this material with light? Yeah. And at a later time delay, 4 picoseconds later, we see a different trend. So as a function of fluence, the system first hardly changes, the scattering amplitude hardly changes, and then rapidly increases above a fluence threshold. And extrapolating from the high fluence data with a linear fit, down to zero change in scattering amplitude, we can extract what's called the fluence threshold. Above what fluence does this change in signal start to rapidly increase? And it appears that this fluence threshold is inhomogeneous. So what's going on? Well, we know that temperature is an important parameter of the problem. So we wanted to analyze how does this depend on temperature. So first, what we're going to do is fix the time delay at 600 picoseconds after we have photoexcited the system, giving it plenty of time to grow and nucleate and do whatever it's going to do. And also not giving it enough time to cool back down to the initial insulating state. So that cooling process takes about 10 nanoseconds. So first, starting from room temperature, what we're looking at is how the signal changes at a single location. As a function of fluence, we see this nice sharp threshold. And as we increase the base temperature, so we're starting at this base temperature and then we're increasing the fluence and watching how the system changes, we can see this nice systematic change or decrease of the fluence threshold with increasing base temperature. All of this is at a single fixed location. Okay. And plotting this data of the fluence threshold as a function of the base temperature, we can see that this is a nice regular linear decrease until a certain temperature where the fluence threshold starts to decrease rapidly. And this can be compared with resistivity measurements on the same film. We see that this kink where the fluence threshold starts to decrease rapidly occurs around the same temperature where we observe hysteresis in the resistivity measurements. So this is around the insulator to metal transition temperature. We can also analyze a slightly different quantity, which is how much the fluence threshold changes at two neighboring temperatures, which we called the photothermal capacity, or C star, in this work. Okay, and the reason for that I'll explain in some detail. Essentially, we see that this quantity is more or less flat until a certain temperature when there's an abrupt increase or divergence of this quantity. We repeated all of these measurements at a neighboring location where we observe some kind of inhomogeneity. And notably, the fluence threshold is higher at this second location. However, this is essentially an offset in the actual change in fluence threshold as a function of temperature has a very similar slope at the two locations. And more notably, the temperature where we observe this kink, where the fluence threshold starts to decrease rapidly, or this quantity C star diverges, occurs around the same initial temperature. So this instability in the system seems to kick in at the same temperature at two locations where we observe an inhomogeneous fluence threshold. I just want to make one connection with this quantity C star and the specific heat, which is maybe a more recognizable quantity in condensed matter communities. So the specific heat has units of cal per mole per degree Celsius. And if you don't normalize that to the volume of material that is being heated, this is just cal per degree Celsius. And that's actually the same units as this photothermal capacity. In this work, we discussed the connection between these two, and in the very specific case that photoexcitation does nothing to your film except for change its temperature and heat the system, these are actually identical. However, photoexcitation can be much more complicated. So photoexcitation can do a lot of things. It can directly change the structure, change how many carriers are in the system, and so on. And in those cases, these are different. And unfortunately, we were unable to normalize and directly compare this quantity, the photothermal capacity, to specific heat. If you could do that, it should be possible to deduce if this is a thermal or non-thermal transition, but it's very difficult to figure out exactly how much volume is impacted by photoexcitation, especially when we have the tip and all of a thin film and so on. And so this connection is only qualitative. Nonetheless, if we plot our data on the same scale, we do see divergence at the same temperature where you observe divergence of the specific heat. Going on to dynamics, what we see is, again, an abrupt rise and then a decrease of the near field amplitude, so a recovery on the picosecond timescale, and then a follow-up increase of the signal. And all of this is fluence dependent. So, so this data, all collected again at a single location in our film, is sort of a summary of how the system evolves as a function of time and fluence. And at a given time delay, say 4 picoseconds, you could take this data and just plot the change in near field amplitude as a function of fluence. And again, you see a fluence threshold. If you look at a later time delay, then you actually see that there's a reduction in the fluence threshold as a function of time delay. And at a neighboring location, we repeated all of these measurements and saw that there was, again, an inhomogeneous time-dependent fluence threshold. So summarizing this data, all in this plot, what you can see is that there is a time-dependent fluence threshold of this system. And at a neighboring location, the system essentially takes a longer time to reach some probability of evolving into a metallic state. So to summarize, what does this actually tell us about vanadium dioxide and tell us about the transition? We have a situation where the system starts in an insulating state, and then after we photoexcite it, the metallic phase becomes preferable. The system can gain bulk energy by transitioning into a metallic phase. However, it takes a long time before the system actually will evolve into this metallic state. At a neighboring location, what we are seeing is that the system actually takes even more time to evolve into the metallic state. The reasons for that are likely because there is some change in the free energy surface, whether that's a change in the bulk energy, a change in the energy barrier separating these two phases, or some combination of the two effects. However, we can't really say. And so this tells us some qualitative information, but it doesn't really tell us what's going on, what is causing the system to be inhomogeneous, and what is actually inhomogeneous. In order to address that, we took a look at several things. So first, we wanted to look at spectra of the near field amplitude. And this spectra shows an edge at a frequency of around 700 wave numbers that comes from lattice vibrations in the system. This is a monoclinic phonon. We observed at room temperature, when the system is a homogeneous insulator, that there was an inhomogeneous phonon spectra. And if you park at a certain frequency around 700 wave numbers and take a map looking at how this contrast appears in real space, you can see these stripe-like patterns. Again, this is all at room temperature, where the system is a homogeneous insulator. Frank Ruda was able to explain this data by invoking twin domains, which are known from TEM, X-ray, and other measurements to be in our film, where the system can form with two stable monoclinic orientations, which are different. And this causes reflection blades of these phonons to project differently onto the AFM tip. These calculated spectra agree pretty well with our data, and so we believe that this contrast comes from twin domains in the film. Now we can compare that, that twin domain structure with the conductivity, which is all we have to do is basically increase the infrared frequency to a higher energy where lattice vibrations don't impact the measurement, and heat up the film a little bit to the point where metallic nuclei first appear in this film. And then we can see increase of contrast, which is indicating the locations of domains in the film, which is inhomogeneous. And we compare that to the location of twin domain boundaries in the same film. And we saw a pretty strong correlation suggesting that these metallic nuclei tend to show up at twin domain interfaces. In the light-induced transition, we compared the conductivity to features that are observed in the AFM topography coming from grain boundaries in our film. And these grain boundaries have perimeters that are highlighted by the white lines. What we can see is that the largest amplitude of the near field signal in the transient state tends to appear in between the grains. So we see the strongest enhancements of conduct transient state and grain boundaries. And while this kind of observation could be impacted by field enhancement with the tip sort of buried in a trench and other things, we extracted the power law of how the area of metal depends on the pump probe time delay. And this agrees with grain boundary driven nucleation and not with other types of nucleation. So it appears that some type of boundaries, twin domain boundaries, grain boundaries, are anchoring nucleation sites in our film and causing the transition to be inhomogeneous. All of that is pretty much what you would expect just from a basic classic nucleation theory, where you can take a domain that emerges and it may have some irregular shape, but in the interior of the domain, you gain bulk energy by moving into a new metallic phase. However, this comes with an interfacial energy cost. In order to form an insulator metal interface, you have to pay the cost of creating this interface. In classical nucleation theory, you basically assume a spherical cow and approximate this domain as just being a sphere with a given radius. And then that competition between bulk energy gain and interfacial energy cost leads to a work barrier, where the system has to put in a certain amount of work to actually move into the new phase. And that delays nucleation. So there is a nucleation rate that depends on the height of this work barrier. Now, the system has a very nice natural way of speeding this process up if there are boundaries in the film, because the work barrier can be reduced by wetting. So if the metallic nucleus forms at a boundary, then the work is reduced and the system can nucleate metal faster. However, in this case, you still have to wait for the metallic domain to grow into the rest of the film. And from this data, we can extract a rate of growth and put a bound on the nucleation rate at a given fluence. So all of this seems to indicate that the system is inhomogeneous, and a big part of that is the presence of boundaries. But this is a complicated system. There are strain fields, there are grain boundaries, there are twin domains, there are possible chemical inhomogeneities and stoichiometry, and all of these things are playing a role. I just want to stress that these are qualitative inferences, and we're really just beginning to learn about nucleation and growth, even of just the electronic transition in these films. The last thing that I wanted to stress is that if you put structures on your film, you change the magnitude of the local electric field, in some cases by a lot. In the terahertz, this can again be factors of 1,000, 10,000. Even in the infrared, we can get modest field enhancement of about 50%. And this field enhancement was actually sufficient to drive metallic nucleation to specific sites, to occur at specific sites near the corners of resonators that we patterned on our film. You can see this in the patterns of the near field amplitude, which agree fairly well with finite element simulations of the local electric field. And this allows us to monitor the growth of metal that we anchored to a specific site in real space as it grows out into the rest of the film. So how do we know this is actually happening? Well, there's two key pieces of evidence if you look carefully at this data. First, if you look at a location in the interior of the film, you see, again, an increase of the near field amplitude, and then a decrease and a follow-up increase. Right after photoexcitation, you have an increase which is linearly proportionate to fluence. And if you look right next to the antenna, you can see that there is an increase that's about 50% higher at this initial time delay, indicating there is a larger fluence or a larger electric field at this location. The second thing is that if you look at some intermediate location between the edge of the antenna and the interior, you can see that first, the change in near field amplitude is tracking what you see in the interior of the film. And then at some time delay, there's an abrupt jump or increase in the signal when the domain reaches this location. So we believe that this metamaterial is anchoring the transition to specific sites, and this may be a nice way to intentionally anchor nucleation to target location and monitor how the system evolves as a function of space and time. So last, I wanted to comment on what we're setting up here at UMD and some of the things that we would like to have a look at. So starting from a physics-focused approach, we're very interested in properties of 2D materials, for example, excitons, how they evolve in bilayer systems and other 2D materials. We're also very interested in studying properties of ferroics. This includes ferroelectrics and magnon polaritons, so magnetic excitations, as well as the properties of correlated electron systems. So this is data from Richard Averett that suggests that not only this nucleation and growth causes inhomogeneity in phase transitions, but also supercooling processes, for example, in neodymium nickelate, can lead to phase separation that creates bottlenecks for how the system can recover back into its parent state. And to address these physics, terahertz spectroscopy is a fantastic tool. In the case of excitons, you can see internal quantum transitions that can directly tell you how information about how the excitons, well, the presence of excitons in a given system and how they are evolving in real space and real time. For magnons, these are low energy excitations. So Ferromagnetic resonances have gigahertz resonant frequencies, whereas antiferromagnets and emerging altermagnets have resonance frequencies in the terahertz. And ferroelectrics have conductive domain walls. Conductivity is a feature that shows up at terahertz frequencies. And so we would like to develop a good terahertz probe that's sensitive. And this is data that we've collected in the physical science complex. This is a terahertz beamline that we have that's been developed by Yulong Dong, a student in my group. And we're also developing tools for microscopy so that we can look at how different systems evolve in real space and real time. So this is an image on bismuth ferrite that was provided by Ichiro Takeuchi, showing rather large patches where there's a pretty significant increase in the near field amplitude. And this was actually not what we expected. We expected sharp domain walls. So we need to dig in and figure out what's going on here. We've also started looking at chiral ferroelectrics that are provided by Shenken Ren. And we're very excited to continue along this path and keep measuring. With that, I'd like to leave you with some of the eye candy from the talk and welcome your questions.
So when you mentioned the first showed the structural and electronic transition and said, a chicken and the egg question, is it meaningful to ask which one comes first, or is there some, energy contribution that each one contributes to the transition? And how do you
ask that?
How do you ask that?
Yeah, so there's many ways to look at it. So from the perspective of technologies, it's meaningful to ask that question in the sense that if you could have the electronic transition occur without the structural transition, you would presumably have to pay less latent heat to produce this transition. So you get the same change in conductivity with less input energy. And the fatigue, which is primarily believed to come from the structural transition, could potentially be better. So from the question of fundamental of the physics of this system, what you have is essentially the electronic transition could be associated with a Mott transition. So the system is a Mott insulator. The structural transition, however, comes with a unit cell doubling and a Peierls distortion that opens a band gap in the system. And so whether that gives rise to the insulating behavior or if it's the electronic correlations is sort of the open question. Now, evidence is increasingly pointing to this being what's called a Peierls assisted Mott transition, meaning both of these things are playing a role. And there's different varying degrees of support for the notion that you can produce the electronic transition, but just at the beginning and just within tiny regions. So a small fraction of the film close to nucleation sites is believed to maybe be a true monoclinic meta. But evidence is still sort of evolving and coming out, and there's always controversies and people arguing both points. Yeah.
So what's the RMS roughness in some of these films, and also for the vanadium oxide, which you showed a lot of? What was the deposition method?
Oh, okay. The deposition method, I have to remind myself because we studied various versions of this. But these are films on R-cut sapphire. The average thickness is around 100 nanometers, and then we have a granular pattern that we can see on the surface, which is about 10 nanometer roughness. So it's pretty rough. Yeah. Okay. But from X-ray measurements, the crystallinity is actually pretty good. So misorientation between the grains is only a few %. Yeah.
Sputtering gives you grains that are about 10 nanometers. So maybe.
So I guess going back to this electron versus structural, I mean, If the electron photon coupling were kind of weaker, the electron thermalization time was small, I should imagine. With your pump probe, you could have heated the electrons and seen something before the phonons had a chance to do anything. So do you have a sense of where that regime would be? I guess you're not in that regime. Right?
Yeah. Okay. So in this what's it called? This is around 60 femtoseconds. So there's a lot of changes that occur in the structure on timescales after 60 femtoseconds. In those first 60 femtoseconds, there's a lot of data on this sort of this regime. What's it called?
You can't see the conductance do anything interesting in that range.
No, there are reports addressing this. So I'm not sure if it's published, but I had a look at a paper recently that was dealing with exactly this, trying to do sub 15 femtosecond spectroscopy to try to look at this regime. And it's certainly an interesting regime. There's also reports saying this 60 femtosecond phonon bottleneck could vary as a function of location, strain field, and so on. And so there's always, there's always room to debate. Yeah.
Maybe I missed it. Like, when you talk about those like ring boundaries, like how are there any understanding in how they're formed? Like, I guess I missed, like, is that something that is just separate, like already in the structure? Like,
yeah,
when you approach this like empty transition, like that is like a kind of pin to this structure, but when that structure is formed in the first place, can you try it?
Yeah. So this is already formed. This is part of just this film, and it depends on the growth conditions. In C-cut sapphire, there are what's it called? So the surfaces are less rough. In TiO2, you can get nearly single crystalline films, and there are bulk crystals that don't have these grains at all. The reason that we studied this was that the sapphire serves as a good heat sink. So a lot of these other variations on the film, heat stays in the system for milliseconds, and that makes it very, very challenging to do near field measurements because you'd have to work with sub-kilohertz sources. And cleaner systems where you have a single crystalline like film would be great. I would love to have a look at those, but it's sort of a question of how to produce that sample. Yeah.
From the point of view of setup of the near field microscopy, how do you decide the location of your detector? Because the scattering is sort of taking place in all directions, right?
So when you're talking about like outside of the microscope, way away from the tip. So the decision of the optics and so on really goes back to Fritz Keilmann's papers, and I'd encourage you to read those. They're fantastic papers, sort of analyzing the dipolar radiation pattern that you get from this tip and why you should put your mirror here versus there. But yes, it just comes out as essentially radiation on all angles, and you collect some of that with a parabolic mirror, send it to a detector, and we do lose perhaps a significant fraction of what is scattered because we're only collecting, a certain angular range, but it's the signal to noise is still decent enough.
And so to sort of create this thing, you would have to place the tape of your you would have to place the tape at all these points at different places.
No, the sample is what is raster scanned. So what happens is you focus the light onto the tip, you align a detector in the far field, and if you'd like to learn that alignment procedure, maybe that would be a better conversation for an in-lab visit or something. I'd be happy to show you. But you align it once, then you align your pump and you look for to maximize this change in near field amplitude, and then everything is fixed. The tip stays in the exact same location. What's raster scanned is the sample. So you change the location of the sample under the tip, leaving the optics and the tip in the same location.
Well, then let's thank Aaron again.
All right.